For this problem, we've got two plates welded together. So we've got a thinner plate on this side. So this is looking section AA, so it's saying this is AA. So it's as if you've cut it along this line. This little arrow pointing down the way, that means you're looking down the way. And so that's what this means. When in an engineering drawing, if you've taken a section, what you do is you put on some hatches to show that you've cut through the material, and that's why these have got lines on them. You tend to put them in different directions for the different parts of a component, so that's just some engineering drawing stuff. So to show a section, excuse me. So to show a section, what you're doing is you're just drawing on a line to show where you're going to take that section, little arrow to show what direction you're going to look in, then you imagine cutting it, and then looking down on that section after you've cut it in half. So the reason we drew the section was to show that the thicknesses of those two plates are not the same. So that means we have to use the main formula, the original formula, which uses the weights or the masses of these objects. The reason you can use weight or mass, they're interchangeable because what will happen is just multiply everything by a scale factor, by 9.81 if you're going from mass to weight. And what you find is that just cancels out at the end of the day. So it doesn't matter whether you use weight or mass. What else have we been told? Two plates. I'm going to assume they're steel. Hasn't told us that. It should have. In fact, it probably wouldn't matter as long as the densities of these two things are the same. So as long as it had the same density. But anyway, we'll just assume it's steel and we'll calculate from that using that. The other thing I've done is I've just drawn on the axes. So we've drawn on some axes and we're going to do everything relative to these axes. You can choose those axes anywhere, but I usually put them, the origin is the bottom left of the object. That way you're going to end up with lots of positive numbers. If you start getting negative numbers, it can get a little bit complicated. The other thing I'm going to do before we start is just think to myself, well, where do I think the centre of gravity would be roughly for this composite shape or composite object made up of two simple objects, two cuboids. So it's probably going to be around here somewhere. It's wanting the X and Y position is all we're going to calculate, although we could also give them the Z position. But for this course, we'll just worry about X and Y. It's going to be around there somewhere. It's a bit like the hammer. So this is pretty heavy. So the balance point is going to be somewhere in here. Might be a little bit more this way, but it's somewhere in there. Okay, so what are we going to do? So first thing we need to do is to find the centroid of the two simple shapes. So we're going to need the centroid of this first shape, and you kind of learn these. It's just going to be, for a rectangle, it's just going to be halfway along the length and halfway up the height. So the centroid will just be sitting here. So that's just from learning those. The other one's going to be here. You can also think of it as where the diagonals cross each other. That's where it's going to be. So I'm going to have a couple of centroids like that. The other thing I've done is I've just put on what these would be in terms of the position on the axes. So we've been given some dimensions. This is 30, this is 10. I'm going to assume it's in the middle. So this is 10 up, then it's 10 thick. So it's 20 here, 30 because this whole thing is 30, and the same on the x-axis. I've just put on what these positions are relative to the x-axis. Then what you do is usually for the position of each, you'll show that as an x bar. So it's called x bar, just a small x usually, for the position of the centroid of the first shape. Now where's that going to be? Well, it's going to be halfway along there, so it's going to be at 15 millimeters. Millimeters. So that's going to be 15. Then up here, interesting, this one's also going to be 15. And then the centroid of the next shape, well, it's going to be halfway between 30 and 50. And so that's going to be 40. And it's at the same point the other way, it's 15 this way. So that's x, we could call that x bar 1, x bar 2. And this is both y bar, it means the bar just means it's the position of the centroid. Y bar 1 and y bar 2 are both going to be 15 millimeters from the origin. So we'll just name it origin like so. So we've got those. You remember that the formula was, so the formula we're going to use is the position of the centroid. So what we'll do is we'll call it the capital X bar for the position of the centroid of the whole shape. X bar is equal to the sum of the small, I don't know why I'm doing it like that. So the centroid of each shape times its, we'll use mass, we don't have to multiply by 9.81. So it's the sum of the centroid of each shape times the mass of each simple shape. And then we're going to divide it by the total mass. And I'm just going to make that a bit thicker. So where does that get us to? Well, we'll start with it. And then we're also going to use the position of the centroid of the whole shape in the y direction is equal to the sum of the centroid of each simple shape times the mass of each simple shape divided by the total mass of the whole shape. Let's get the masses first. So we'll call this shape 1. So this is going to have a mass m1. This is going to have a mass m2. Easiest way to calculate this. Okay, so what I'll do is I'll just calculate the mass of each of those shapes. What I'm using is, I'll probably use density, and you can remember it either way, but I'm going to 7850 kilograms per meter cubed, or it's 7.85 grams per centimetre cubed. Now, usually engineers in Australia, they don't use centimetres, they use millimetres, but in the case when you're working with density, it can be easier. So I'll go through and calculate the masses of these two shapes. What I'm going to do is I'm going to convert each of these to centimetres, so that's going to be 10 centimetres. So for the volume of this, I'm going to do 1 centimetre, 1 centimetre times 3 centimetres times half a centimetre, then I'll times it by the density, and then I'll do the same for the other shape. So I'll just get you on the other side of the fast forward while I do that. So I've now got the masses of those two shapes. So then we're going to use, then I need to just, well, we already know the centroids as well. So we know where the centroid of this simple shape here is. We know where the centroid of this simple shape here is. So now we're just going to substitute those into this equation. So what we're saying is, so the centroid of the whole shape is just equal to the sum of the masses times the centroids of the simple shapes. So we're going to do x1 centroid times mass 1 plus x2 times mass 2, the mass of shape 2, so the mass of the bigger block, divided by sum of the masses, so m1 plus m2. So, and then your centroid in the y direction is just going to be equal to the centroid of each shape times its mass. And then divide it all by the sum of the masses again. Okay, so I'll just substitute those values in, and then we should get an answer. Okay, so I worked through those calculations. So the sum of the centroid of each component times the mass of each component, this looks like a capital M, it should just be a lowercase m. And so I've added up those, and then I've added up the total mass of both of the components and divided those, and you get the centroid is at 35.69 millimeters. Okay, so I use centimeters up here, but that doesn't matter. It was just to get a mass. As long as I use the same units everywhere within these equations, I'll just keep the same units at the end, use the same units for mass as well, right the way through. So always don't use kilograms for M1 and grams for M2 or something silly like that. And so we've got a mass for each component, so we've got the centroid of the overall object here. One thing to note here is that, if the centroids of the two objects are at the same level, then the centroid, or the center of gravity, or the centroid, kind of the same thing, but the center of gravity of the whole shape in that direction will also be the same. Just to see why that is, well, what you could do here, just mathematically, what you could do here is you could take out the 15 as a factor. So that's the same as 15 times 11.78 plus 56.52, and divided by the same thing, 11.78 plus 56.52. So those two things cancel out and you just left with the number. And so if both components have a centroid that's at the same position in one of these axes, then the compound object or the composite object will also have a centroid at that position. And you can figure that out by balancing. Like if you were to turn this the other way up and put your finger under it here and balance it, you put this on top and it would balance, and then as long as you put the balance point above that for the next shape, that would also balance. So it makes sense intuitively as well. So that's us got our position. So just capital X for the compound shape. And so where did it end up being? Let me just take these off, or will I? I'll do another one. I might change its color. Hopefully this works this time. Yay! And make that red. So for the compound shape, the centroid's somewhere about here, actually. So it's about 36, isn't it? So it's about here somewhere, which is not far away from where I was guessing it would be. And so it looks like it's about right. Okay, that's that one. We'll get on with the next one.